Okay, Bogdan.
Okay.
Fine.
So, good afternoon, ladies and gentlemen. Welcome to the 32nd seminar of Metamaterials organized by MetaMAT. Today, it's my pleasure to introduce Professor Hu from BIT in China. Professor Hu is going to talk about elastic metamaterials and their application for wave control. So, Professor Hu, it's your turn, please.
Okay. Thanks, Mohamed, for the kind of introduction. It is my honor, and I'm very happy to have this opportunity to present some of my works on metamaterials. I think the three organizers really have a very nice actions to promote the exchange of in the metamaterials community. So I come from the Beijing Institute of Technology. My talk today is on the elastic metamaterials and their applications. So this is my outline of the talk. So I will firstly give some words on background, and then I will provide the three examples to show how to design microstructures to, for example, to make the material to refract the elastic waves in a negative way, and also how to design the microstructures to filter the elastic waves. Finally, give an example how to design an elastic cloak. Okay, so we know for a solid, they support two kind of wave depending on the particle motion and the propagating the direction of the waves. Okay, if the particle's motion is perpendicular to the wave motion, so we call it transverse waves. If the particle motion is lying the same as the wave propagating directions, so we have longitudinal waves. Okay, to analyze the waves, we have to assume applying waves or a block wave solutions, and then we put this mod into the equation of motions. And in two dimensions, we can have this kind of eigenvalue problems. So the materials constants is encoded in this coefficient. So we have eigenvalue problems, and which, if we have non-trivial solutions, so the determinant of this matrix should be 0. So we have a relation between omega frequency and also the wave vectors, which is a very important relations called dispersion relations, which describe the wave characteristic in the materials. So we can analyze these relations in two different ways. First, we can assume that the frequency is fixed. So we have iso frequency curves or equal frequency curves. For example, for the T wave, for the longitudinal waves, so we have a wave vector here, and we have the energy flow here, because for isotropic materials, they are in the same direction. We have the the arrows here means the particle motions, which is the same direction as the wave propagations. This is for the transverse waves. We can also plot the function of a k along the Brownian boundaries as a function of the frequency. Sometimes if we're given a wave vectors, we cannot find the frequency. That means the wave cannot propagate. This frequency cannot propagate these materials. That means we have a bound gaps. So in order to look at in more details how the materials interact with the elastic waves, so I plot as a function of a density and also the bulk modulus of the materials. For the classical materials, these two parameters are positive. So the wave can propagate inside of these materials. And normally, the wave vectors and also, oh, sorry, because it doesn't, this is a movie, but it doesn't work. I have to change the key. I think it should work. No, so I change it back. Okay, we have another three sectors that in these two sectors, one of these parameters are negative. So we see that from the dispersion relations. So the square root is the k is imaginary. So for these two sectors, the materials cannot support the wave, cannot support the waves. So we have a bound gaps here. There's another very special region that those parameters, the Bark modulus and effect mass density of the materials are negative. So the ratio of these two parameters remain positive. So the K is real. So that means the materials in these sectors can support propagating waves. But here we have to choose a negative sign. So that means that the group velocity and wave propagating directions are opposite each other. So if we have waves incident from classical media, that is positive with positive parameters, and on the bottoms we have a negative, double negative medias, because we have here, for example, a wave as incident from top, and things for the double negative media, the energy flow directions is opposite to the wave propagating directions. So in order to conserve the wave vectors along this line, so the wave must be refracted in the same side compared to the normal of this part. So we have the negative refractions. So in order to design metamaterials to have a negative refraction for elastic waves, so we have two things. The first, we have to design microstructures to have a negative mass, and we have the second thing is to have negative modulus or Bark modulus, and we turn these two at the same frequencies. Okay, the first things for the negative effective mass, in fact, in 2000, Professor Liu and Champagne proposed the mechanism, resonance mechanisms, to realize the negative mass density. So the basic idea of the method is that we have a system of a multi-degree of freedoms. So we have some are macroscopic, so that means we can be observed, and some are hidden, so they cannot be observed. So if we want to project the total momentums on the observable parameters, so we define the mass effective masses. In some cases, we can see from this picture that in some cases we have a resonance, so the hidden elements can have a very large amplitude of velocity, and they move out of phase. So the total momentums may be the different directions compared to the macroscopic velocity. So we define a negative mass density here. So in order to verify it is correct or not in the mechanical systems, at that time I started my research on metamaterials. I asked my students to construct an experiment to show it is the negative mass is correct or not. So we constructed a mass in mass model, so that we have here we have a unit share here. It's a mass in mass model. So middle is can move is connected with the outer one here. So we have a 6 units, and all the units are lifted by air tracks in order to avoid frictions. Okay, so two frequency we choose. The first is a 3 Hertz. So we have a wave. We have a wave inside of these systems. I'm sorry, because when I change this mode, I cannot. So the movie cannot work. Let's see now.
Professor, could you try with not a full screen?
Full what?
It should not be perhaps a full screen.
Or maybe you click right with the mouse.
Sorry, but because it is not the mouse key, so I want to come back to the mouse key, but it doesn't work.
Maybe just press escape and you get out of this mode.
Sorry. Oh, I'm sorry. I just
No,
this
no
way.
problem.
Okay. So I use this key is better. Okay.
Yes.
So I choose the frequency 3 Hertz. So we have a wave here. So we can see that the wave can propagate inside of this system. And if we choose, for example, the 6 Hertz, so we the frequency is located with the band gaps. So as the prediction, so we cannot, the wave cannot propagate inside of this system. So this experiment show that the concept of a negative mass work for the mechanical systems. So we have a negative mass, we have also the positive mass. So we have a zero mass, of course. So I ask my students to look at what happens if we have a zero effective mass. So theoretically, if we have a zero effective mass, so the wave velocity inside of these materials become infinite. So I ask him to do experiments. And we see that it's the frequency where the effective mass is zero. So this system move as a rigid bar. So we cannot see the hidden mass here. So there's a not phase change inside of the systems. And also that we can have a full transmission. So that the excitation here can fully transmit to other side. So these properties can be used to make acoustic superlens. Okay, so this is the first parameters that we needed to negative refraction. And the second properties that we need is to produce a negative effective modulus. So for the acoustic material, for acoustic waves, it is relatively easy to induce a monopolar resonance because we can put some particles inside of liquid materials. We can easily produce monopole resonance. But for the solid materials, it's very difficult. So we propose another mechanism using the rotational resonance. So we consider a unit shell like this. So we apply a force from on this unit. So we can imagine that we compress this unit and this disk rotate anti-clockwise way. So they push this point outside. So just like we push the unit, but the unit expanded. So we have a negative Burke modulus. Okay, so we have a negative mass density. We have a negative Burke modulus. So we can make these two together. So we have as expected, we can calculate it, for example, the bond structure here. This is the bond structures. This is the mass density, the effective mass. This is the effective modulus. So we can see that within the overlap region, that the mass density and also the modulus are both negative. So we can have a propagating wave here with a negative slope, just as expected. So this is a toy model. In order to do experiments, so we have to fabricate, we have to propose a realistic models. Here, after some tests, we arrived this kind of a material design. So we take a plate, we make this kind of microstructures that in the middle, this is the unit shell. In the middle, we have a heavy mass. It's connected with the background plate by these three ribs. These three ribs are formed in a chiral way. That means we have a wave in these directions, and this heavy mass can translate it, can move in this direction, and can also rotate. So with single mass, we can produce both negative mass density and also negative Burke modulus. And this idea is confirmed by the bond structure here. So this is the pink region is the negative mass density, and this region is the negative modulus. So in the overlapped regions, we have propagating waves here with a negative slope. Okay, so before the experiments, so we make a simulation, a transit simulation. So we take triangular forms with the microstructures that we proposed, and then we send a cosine beam here. If we have a negative refractions, so the wave should be reflected in this way. So if it is positive, it will be reflected in this way, okay? So if we choose the frequency f equal to 43.8 gigahertz, so we are situated in the region that both effective modulus and mass densities are negative. So we have a negative refractions. Here is the simulation results. So we can see that the wave is refracted in these directions. It takes some time to be stabilized. Okay, so we have a negative refractions. And if we choose for the same materials, we choose another frequency. Since in this frequencies, both the modulus and the mass density are positive. So we have a positive refractions. So that means simulation prove our design. So in order to do the experiments, we choose this experiment is conducted by in US by Guoliang Huang. So we catch these patterns, and we stick the different on the top and the bottom the piezoelectric pitch to generate S0 mode. So we think it can be approximate the bark longitudinal waves. Okay, so we send a signal here, and we scan the motion in this area. This is experimental results. This is simulations. So the experiments show clearly that we have a negative refraction, which agree quite well with the simulations. Okay, so that is the first example. I will show you that we can design the microstructures and to have both negative mass density and modulus. In these cases, we can have a negative refraction for elastic waves. So the second examples, I will show you how to design the microstructures and which can feature the elastic waves. So we ask the following questions. For a solid, I just mentioned that for a solid that they can support two kind of waves, longitudinal and transverse. And for the liquid materials, they support only one kind of mode, one kind of waves. So only longitudinal waves, okay? So the liquid, in fact, serves naturally a feature for transverse waves. So if we put the solid and the liquid together, and we send a mixed mode, and only longitudinal wave allowed to trans through these materials. Okay, the question that we ask is that, can we make a solid materials which function as the same as the liquid materials? That means can we design a solid materials can only let the longitudinal waves to pass through, and then the shear waves is bounced back. So there's the first questions. So that means, can we make a solid liquid? The second question is that, can we make a solid materials to only let the transverse waves to pass through these materials, and the longitudinal waves is bounced back? So these two questions. Okay, in order to make the problems as simple as possible, we consider the following situations. So we have two semi-infinite materials, which is isotropic with elastic tensors written in this way. And we want to design these materials layers. These materials is anisotropic with principal x angle θ2 compare against the horizontal directions. So in order to simplify the problems, we assume that the anisotropic material, the density of these materials is the same as the background materials. So that is for a simplification problems. Okay, so for these problems, we can have the analytical solutions. So we can calculated analytically the reflected longitudinal wave, transverse wave, transmitted longitudinal waves, and the transverse wave. Okay, so for now we consider the first cases. So we will find the materials necessary for example, if we let the air wave, that is the longitudinal wave, to pass through, and the shear waves is bounce back. Okay, so we can, using these analytical solutions, and finally we arrive these kind of materials parameters. So that means that the theta 2 is 0. So that means these materials, the principal axis of these materials is aligned in the horizontal directions, and these materials, the property of these materials is like this. There's some special point here. So we have another shear modulus of this material should be 0. That means we have extremal materials I will talk about in the following slides. Okay, so now let's consider the second cases. So we let the transverse wave to pass through this layer, and the longitudinal waves is bounce back. So we use the same technique because we have the analytical solutions, and we found that for these materials, the principal axis have an angle theta 2 determined by the background materials, and the materials property of this layer look like this. This is also have a very special value, that is 0. So this matrix is not determinate, so they contain some 0 eigenvalues. Okay, these problems we code is coded by Newton and Chekhov, code to the extremal materials. So if we have a generalized Hooke's law, so the elastic tensor of this of the elastic tensor has 6 eigenvalues and 6 eigenvectors. So if one eigenvalue is 0, we call this material as a unimode. If 2 are 0, we call this a bimode. So if 5 are 0, we call it the pentamode. So it is extreme materials contain some mechanism. So contain some deformation without energy. Okay. So the materials in the previous slide is a pentamode materials in 3 dimensions. It also called the bimode in 2 dimensions. Okay, so things I should we come back to slide here because there's a negative sign here. So this materials is has a negative Poisson ratio. Okay, so we call this a negative type pentamode materials. If we plot the eigenfrequency of these materials, we found that along these directions, it supports only longitudinal waves as we obtain. And also we found another particular angles here that the polarization is perpendicular to the wave directions. So that means it's these special angles, these materials support only shear waves. So the longitudinal waves is not allowed. So this angle exactly we determined for the case 2. So that same materials, if we change an angle theta 2, and this allow only the transverse waves to pass through this media, and the longitudinal waves is not allowed. So we found exactly the same the materials parameter necessary for the case 2. That is the mechanism. Okay, so in order to find the microstructures, so that is the previously we have the homogeneous materials necessary for the 2 situations, case 1 and case 2, and now we want to find the microstructures to make the experiments. Okay, we started from hexagonal structures with some mass inside. This is proposed initially by Dr. Chen, E. Chen. So this mass here is used for adjust the mass density of the unit shell. And then we can calculate the effective answer of this lattice. And then we optimize these parameters in order that the effective property of this lattice to satisfy the materials property that we derive from the case 1 and the case 2. Okay, so finally, for the case 1, we arrive for the case 1 that we have a materials only let the longitudinal wave to pass through, and the shear wave is bounced back. So we arrive this kind of a microstructures. And in the experiments, so because we have some teeny, this is not straight. So in the experiments, so we smooth out these teeny structures. So we have this kind of a microstructure here that we designed the layer that for the case 1. Because in the analysis, we assume that the mass density is the same as the anisotropic layer. So for the aluminum matrix, so we have to put some hole in order to have the same mass density. Okay. So for the case 2, it just rotated these microstructures in this way, rotated at angles. Okay. So that is the microstructure we design, and now we will do the experiments. So we make 2 aluminum beams here, and in the middle we make 2 kind of a microstructure here. So this is for type 1, this is for the type 2. For the type 1, this is very thick. It is 5 millimeter. This is only 2 millimeter. So we here in this end, we choose some special piezoelectric actuators for the 2 kind of waves, for longitudinal waves and also for the shear waves. Okay, we choose the crystal with different coupling coefficient, and here we use the laser vibrometers to measure the response. Okay, here is the results. So for the type 1, remember that for the case 1, we let the longitudinal wave to pass through, and the transverse wave is bounced back. Okay, so we can see that we cannot see the signal for the transverse wave, and for the longitudinal waves, we find is the wave is propagating through these materials. And for the case 2, we rotated an angle here. So the longitudinal waves is stopped, and we can see that we can see a transverse wave pass through this medium. So exactly what we want. So this is a reference cases. So we have longitudinal waves, both longitudinal wave and the transverse waves are allowed to pass through these aluminum mediums. I must just stress that this design is broadband. So because we do not use any resonance mechanism. So this mechanism is broadband, so can support very low frequency waves. Okay, so that is the second example that we designed the microstructure to filter the elastic waves, to choose which kind of waves can allow to pass through or which wave is bounced back. So the third example, I will show you how to design an elastic cloak. Okay, so the cloak, so waves, when they come to scatters, some wave scatters, and they leave some settle behind the scatters. Okay, so if we can design a layer coated these scatters, so guided the wave to go around these scatters. So there's no scattering and no shadows, and this is called a cloak. So the tools to design a cloak is called the transformation method. So design a cloak, the essential things is to find the materials distribution in a layer that to guide the wave to go through these regions. In order to solve these problems, so we constructed auxiliary problems that we have a uniform space, the wave is propagating in a straight way. And then we make a change of a variable which can be characterized by distortion of a space. So we distort the space to make the wave curve exactly what we want, okay? If before the change of a variable, So the governing equation here is the Maxwell equation is the same before and after the change of our variables. This change of variables are characterized by distortion of space. Okay, so we can use the new expression of a material parameters. For example, here is a permeability, a permittivity. We can use these materials as the real materials distributed here that they guided a wave to go around these materials. So the same form of the equation after change of our variables is called form inverse. These materials, if we can do that, if the materials are valid, because this new expression is related to the distortion of space. For the electromagnetic waves and the acoustic waves, it is relatively easy because it is simply to extend the permeability and the permittivity to a negative value, or for the acoustic waves, it is simply to extend the mass density from a scalar to a tensor values. This is the first, I think, so the first cloak, electromagnetic cloaks, effected in 2002 by Strack and Smith's group. However, for the elastic wave, the situation is quite complicated. If we follow the same idea, so the materials are much complicated. For example, depending the gauge that we choose, the gauge is the term given by Professor Norris. So if we choose this kind of gauges, so the materials necessary is very complicated. For example, the stress is dependent on the strain, and not only the strain, but also the velocity. The momentums depend on the velocity and also depend on the strain. So it is the cold Willis media. It is very difficult. It is under intense research, but it is not mature enough to be used to design a cloak. So the second approach is proposed by Brian and also the one of our organizer, Sebastian, in 2009, so that they choose this kind of a gauge that they have the same form as the Cauchy elasticity. However, the elastic tensors has not a minor symmetry. This material is also very difficult to be realized in practice. The third way to do that is proposed by Norris, that we choose a special materials that we only analyze some kind of pseudo-acoustic waves, pseudo-elastic waves. Okay? So we choose pentamode materials, and we follow this idea that Dr. Chen Yi proposed, did experiments to make a cloak with a pentamode materials. This is a cloak. In the experiments, we cover the top and the bottom in order to avoid the water to penetrate this cavity, and then we put this cloak into a waveguide specially designed, and the whole waveguide are immersed in anechoic water ponds. This is the results, experimental results. So this is a cloak here. So this is no cloak, it's an air scatters. So we can see that there's a large scattering shadows behind here. And with the cloak, the shadows is largely reduced. So this is work quite well for pentamode materials. Today, I will talk about this method. So we try to design a materials without without minor symmetries. Okay, these materials I code asymmetric metamaterials. It is also called polar materials by Houxin and Guoliang Huang in their papers. And these materials has a very nice property. They can be impedance merged with Cauchy materials. If, for example, if we have Cauchy materials here, and if we send a wave to another media, another materials, if we can be made impedance merged with these Cauchy materials, these materials cannot have minor symmetry. So that means we have to drop off the minor symmetries. In fact, for this kind of metamaterials, I called asymmetric metamaterials, it has been used for a long time in the mathematical models in a computational elastic waves to, for example, to design a PML to perfect much layers. Okay, so now we will look at what this kind of materials look like if we want to design a cloak. So we follow the method proposed by Brian and Sebastian, that in the cloak layer, the density should be varied in these forms. And the density and also the elastic tensor of these materials should vary in this form also. And these materials has not minor symmetry. Okay. So we have a delta depend the position in the cloaking layers. Okay, so what property of these materials have, or what wave property of these materials have? So we can derive the dispersion curves. And in these materials, they support two kind of waves, S-dominated or P-dominated. So the most important things is that for these materials to realize the elastic cloaks, the equal frequency, or we call it isofrequency curves, have this kind of these shapes, have a similar to ellipse shapes. That is very important to design the elastic cloak. Okay, so in order to design the materials to realize the cloak, so now let's first to look at why we should have the minor symmetry. So for the Cauchy material, Cauchy elasticity, we have a generalized Hooke's law. So we'll see that if we consider a system that is conservative, so that means for the materials we have not energy gain or loss in these materials, so that we can have energy potential for these materials, and we have a nice property. We can change, for example, the differential operators here, so we can have a major symmetry. So if we consider a conservative system, so we have automatically major symmetry. Okay, so if we consider a materials point here, it is infinitesimal small. There's no body torques, no surface torques on the elements. So if we use the balance of angular momentums, and then we arrive the symmetry of the string. So we have a minor symmetry. Okay, so in order to break, so our job here to design the elastic cloak. So we have to design our materials without minor symmetry. Okay, so in order to design these materials, so we have choose the second point as a target. Okay, so now let's look at the way to produce a symmetric stress. So the first way, very simple and direct way, is to apply some body torque inside of materials elements. This can be done in fact very easily. So what we can, for example, we can put some magnet inside of a material shell here, and this magnet is controlled remotely by the magnetic field. So we can provide a torque. And we can also use grounding mechanism like NASA and Lianhua has done, and they have did very nice works and also experiments for static clocks. But this method depends on external efforts. So they have provided a grounding mechanism, a grounding method, or be controlled externally by magnetic forces. But here I will look at another mechanism. Now let's consider if we let these elements to rotate with an angular acceleration. they need a moment. This moment is dependent on the areas of the elements, but we show that it is a high order of, so the moment necessary to produce alpha is the angular accelerations. Is a high order, so the moment is a high order of the areas. So if we do the summation of the torques produced by the shear stress, and also to accelerate these elements, because this is a high order of the areas, so it can be neglected. So we have to have the symmetry of stress. Okay, so but this provided the indications how to break the symmetry of stress. So the idea is to increase or to amplify this M. So the idea is that we put a hidden mass here with a torsion spring. So it the rotational resonance, they can provide the torque that we need. We need to break the symmetry of stress. Okay, so this mechanism is exactly the same as the mechanism to produce negative, effective negative mass, and also the effective negative modulus. Exactly the same. So we produce a rotational resonance. They provided a torque. So this method is I think it is depend only on the microstructure themselves without any external assistance like the previous method that I explained. Okay, in order to test this idea, so we propose a Massspring lattice like this. So we have in each unit shell, so we have a 4-point mass, and we have a rigid elements here in order these rigid elements to provide the rotation. Okay, so rotation here. So we have in this unit shell we have 5 parameters. The 3 are hidden. These parameters are microscopic, so that is can be observed outside. So for this lattice models, we choose a unit shell, and we can calculate easily the Hamiltonian of the systems. Then we can calculate the wave equations. Okay, so we can express these 3 hidden variable, we call it local variable, in terms of a macroscopic one, and then we replaced these 3 hidden variables by the macroscopic one, and we arrive very complicated wave equations. Then we can use the Taylor expansion method. We expanded the displacement to the second order, and then we put into the wave equation in this slide. And finally, we arrived at a homogenized equation, a wave equation for the lattice models. And fortunately, if we look at the 2 coefficients here, 2 components, C1, 2, 2, 1, it is different from C2, 1, 2, 1. That is exactly what we want. So this media, this the Massspring model we proposed is a symmetric metamaterials that we want. And also they have a very nice property that this component is related to this component by a ratio. This ratio is dependent on the shape of the unit shell that we proposed. So it fits exactly. This matrix is the matrix to realize the elastic cloak. So we can see that we can easily turn the shape of the Massspring models to satisfy the form, the matrix form, to realize the elastic cloak. Okay, so these homogeneous models is correct or not. So we can do some block solution. We calculated the bond structures. And here is the results. We have the bond structures with the Massspring models and with also the homogeneous models. So the red line is the homogeneous model, and the dashed line is the exact solutions. So that is based on the block solutions. Okay. So this is the effective density. This is the effective P-wave modulus. This is the effective shear modulus. Okay. So remember that to have the property, the wave property of the materials to construct a cloak, the equal frequency curves should have a similar double ellipse shapes. Okay, so we can say which frequency satisfy this condition. If we look at this region, so the equal frequency or the isofrequency curves look like this. It is not okay. And if we look in this region, we have only one waves here, so it doesn't work neither. And if we look in this region, we look at the optical branch, so we have a double ellipse shapes. That is exactly we want to make elastic cloak. Okay. So before making the cloak, now let's consider make a check. So we design a perfect match layer. So that we design a materials which is impedance merged with the Cauchy media. Here is the result. So we send a shear wave here. So we see that there's not refraction. They can pass through these media. So that means the discrete model we proposed work quite well, at least to be impedance matched with Cauchy media. So in order to make the cloak, so we have to discretize the continual variation of the cloak by layers. So we along the radial directions we divided, I think it's a 30 layer. Along the hook directions we divided 70 sections, and in each sections we have to adjust the shape of the unit shell and also the parameters of the mass and the rigid elements in order that to fit the density and also the elastic tensor that are needed to construct this cloak. This is not easy, but fortunately my students work very hard and clever to make it automatically. Okay, that is the results. So here's a cloak that we designed without the cloak. So we have a void, we send a P wave, and we send a S wave here. So we can see clearly there's very significant scatterings. Here is a Massspring cloak that we designed here for the P wave, so they can pass through this cloak without scattering and without shadow. This is for P waves. This is for the S waves. So that means the cloak that we propose can work quite well, but it is only a Massspring model. It is very difficult now to make experiments. Okay, so I think I should summarize my talks. So my talks, I explain how to design a microstructure of materials to control elastic waves. I explained that by 3 examples. The first, to design the microstructure to control the effective material properties in order to have negative refractions. The second example is to design the materials to control the polarization of elastic wave. So I give the example as elastic wave featurings. The third, the last example is to control the materials distribution, and the example is elastic cloak. Okay, so the works that I taught today is a collective work. So it is mainly made by my PhD students, my colleagues, and my collaborators. But here I give some reference of related to my talks. If someone wants to learn more, they can read these papers. Okay, that is all of my talk. Thank you for your listening.
Thank you very much, Professor Hu. It was a very nice talk. So now we have time for questions. So I would like to remind all participants that your microphone is off and you have to put it on in order to ask questions. You don't have to raise your hand, just to go ahead and ask questions that you have.